So it's my pleasure now to announce the next speaker, Chi Yin. He's an assistant professor at the Electrical and Computer Engineering Department of Princeton University, and he obtained his PhD degree in computer science at the University of California, Berkeley. His research mainly focuses on theoretical machine learning with special emphasis on non-convex optimization and reinforcement learning. In today's talk, he will be talking about when it's partially observable reinforcement learning not scary. So welcome, and please start your talk.
Thank you very much for the invitation, and thank you for the introduction. First thing is I hope everyone is fine with the screen sharing and the sound. Is everything okay?
Yes.
Okay, that sounds great. So yeah, so I think today I'm mostly working on like reinforcement learning theory. So today I will talk about our new development for partially observable reinforcement learning. And I think we know there are so many theoretical works on reinforcement learning, but most of them are on the fully observable case, like in the Markov decision process, which assume we fully observe the states. Well, in practice, there are a lot of problems which is partially observable. And we will talk about some new development which show some initial positive results on that kind of more challenging partially observable setting. I think it's related to SAFIL in the sense I think a lot of times we develop algorithms with heuristics, and with this reinforcement learning theory, we can basically have algorithms which are reliable or guarantees to find some optimal policy. So we we know what is the scope and what is the conditions we would expect our algorithm to work, and in what kind of scenario the algorithm will not work. And today we'll clarify that on the partially observable scenario. Okay. First, I would like to thank my wonderful collaborators, and this is a joint work with Qinghua Liu, my student at Princeton University, and Alan Chuan was an undergrad student at Princeton. Now he's heading to Harvard, and Akshay at MSR, Sham Kakade from Harvard, and Csaba from the University of Alberta, and also DeepMind. Okay, and so we're going to talk about partially observability today. There are a lot of reinforcement. As I said, previous reinforcement has mostly focused on a fully observable scenario. However, partially observable setting is like ubiquitous in the modern reinforcement learning. For example, if we want to play some card games like poker, the state will be the cards of on my hands, also on my opponent's hand, but I will just hide the cards on my hand, so it's not revealed to the opponents. So each player will only observe the part of the states of the system. And it's similar for robotics tasks. If we only have like a first-person camera, which you will only able to see the front of the robot, and you will not able to see like what is on the side and what is behind the robot. So this is again a partially observable problems. On some other like strategic games where you have some war frogs, so you only see some neighborhood around your units. And even for some like social games like this hide and seeks, I think they're specially designed so that each agent is only able to see some neighborhood, local area around it. Okay, so today we're gonna, since this is like a reinforcement theory talk, so we're gonna rigorously formulate this partially observable problems by the popular model called partially observable Markov decision process, which is basically standard Markov decision process, which has states and action, and state has a Markov structure. But in addition to that, we have the observations. So we have the emission matrix. Every time this state will generate some emissions, and the observations are not necessarily Markov. So we can think this POMDP model as this MDP, which has a state and action with the emission, with the state going to observation, and we only observe this observation, so we no longer see the states. And we can also view this POMDP as another thing, which is a hidden Markov model, which is basically just state and observation together without any action, and then we adding this action to it. So this is like we can have two views of POMDP. So we know POMDP is definitely much harder than both MDP and hidden Markov model. Okay. So there are a lot of unique challenges in dealing with this partially observable reinforcement learning. We can just first consider a simple scenario where we're in a tabular scenario, so that we only have finite number of states, actions, and horizons. So for the tabular Markov decision process, which is in a fully observable scenario, we have a lot of like tons of efficient computation and statistical efficient result. Like we have the complexity, everything is polynomial in terms of the number of states, number of action, number of horizon, and we think we can learn them efficiently. However, this is not the case for POMDP, because in POMDP, we don't really know the underlying states. We only see the observation, which only reveal the partial information about the states. So in that kind of a scenario, we first need to reason about the states. But here, because we only see observation, so we're no longer sure whether we're in some deterministic states. We can reason about some belief over the states. That is like we say, okay, by observing something like this, we might with 1/2 probability in this states, with 1/2 probability in some other states. And the second thing is because we need to reason about the beliefs, and then when we need to make some action decisions, we actually need to maintain some memories about the past histories. Like when we play poker, whatever my opponents do in the first hands or in the second hands will actually kind of tell something about what he will do now, or what will tell us about something, like reveal some information about what might be the cards in their hands. So whatever the action or decision I make will depend on the entire history instead of the current states. And we will deal with all these challenges while exploring the environment. So this is much challenging. And it turns out there are a lot of hardness results, which says in general, you cannot learn POMDP in polynomial samples. So this is dramatically different from the fully observable scenarios. So the hardness results, first thing is computational hardness results, which says even forget about anything about statistics. For example, I have infinite samples. I already know precisely what is a model, like what I know precisely what are the transitions and what are the observation, what are the emissions. Then in that kind of scenario, planning itself is also hard, which is just based on these models, I want to compute optimal policy. So we know if we just want to compute the general optimal policy, it's p-space complete. That is, and if we don't care about the optimal policy, we only care about so-called memoryless policy, which are the subclass of policy which make actions only based on the current observation at the current step. Even want to find the optimal policy in this restricted subclass is still NP hard. So basically, we cannot have any polynomial time algorithm for any of this. And above this, there are also statistical hardness. That is, in reality, we only observe samples, we want to observe trajectories of the real environment. We don't really know what is underlying dynamics. So we want to ask how many samples we need to learn POMDP. It turns out learning POMDP, even if I have infinite computational resource, would still require some exponential number of samples. Here, A is number of actions for each for the agents, and H is the horizon of this POMDP. We will talk about the details later. So basically, it says both computation and statistical are hard for POMDP. And this has been essentially the state of art in theory community for decades, and which we kind of believe POMDP are not solvable, and we should not consider this problem. So that's also the main reason why so many existing results on reinforcement learning are purely focused on the fully observable scenario. It's not because POMDP, like partial observable, are not important. It's because it's just too hard and we don't know how to do it. So today we will provide some initial steps on addressing the statistical efficiency. Okay, so we will deal with the second problem. So of course, the hardness result is always true. So we cannot just break this hardness results. But what we will do is those hardness results are actually worst case in nature. So they are saying like there exists some POMDP which are extremely hard. We cannot learn it without this exponential number of samples. But in reality, we can expect a lot of the real partially observable problems are not those kind of worst case instance. So we want to develop more like a better theory, which can have incorporate some structure, which are always true, or most likely true in practice. So which is like will empower this statistical tractability. So we will decompose this problem into two parts. The first problem is about identifying some problem structure. Can we identify some rich subclass of POMDPs so that it will be rich enough to cover a lot of the practical applications, but it's also, on the other hand, statistically tractable. And the second problem is once we identify those subclasses, can we develop some very simple algorithm or very good algorithm, efficient algorithm that can efficiently learn this rich class? Okay, two problems. One is problem structure. The second problem is the efficient algorithms. So today we'll deal with both in this talk and see how we develop theory for POMDPs. So before moving on to the formal theory, I want to formally set up the what do we talk about a POMDP. So as we said, a POMDP is basically just MDP plus some emission. So formally, we have several components. The states we have POMDP can be specified by this like S is a set of states, A set of actions, and O is a set of observations. And as we see, observations are what we can see, and these states are like hidden from the agents. And similar to MDP, we have these transitions, which is at every steps, we will have a probability which transition from the current state S and the current action A to the next state S prime. And in addition to that, we have an emission probability, which is a condition on the current state at S, which is at state S. What is the probability of observing some observation O? And we will also have some initial distribution over the states. And we will assume the reward is a function that is mapping from observation to 0, 1, which basically says my reward will be contained in observation, which is like true in most kind of scenario. We will always observe the reward. And we're in this episodic setting, so we assume each game or each run, each episode will end in H steps. So basically, we have S1 to S2, finally to SH in H steps, and then this entire episode is done, and we will restart another game. Okay, so these are basic setup of the POMDPs. And once we have the basic setup, we'll, similar to reinforcement learning, we'll define the concept of policy and the values. So policy in the MDP is basically a map from the states to action. Different from the MDPs, here the policy, as I said, because it's partially observable, so we no longer observe the states, we only observe the observation, which is no longer Markov. So in general, we need to consider policy that is history dependent. So the policy now will be a map from the entire history up to step H, which is like all the previous thing, O1, O2, A1, A2, till OH. Okay, so all the entire history up to step H. Map from this history to an action. This is our current policy. And the value is basically, we will define value as a total expected reward if we execute this policy pi from the start to the end. Okay, so this will develop, and this will define a value for each policy. We no longer define some value for each state. It's just a value for each policy. So the objective is clearly very similar to MDP, to reinforcement learning, is we just want to find an optimal policy pi star so that I can maximize the total expected reward. Okay. So this is a basic setup. And as we previously explained, if we just want to find the optimal policy for POMDP, in the worst case, we will incur some exponential number of samples. That is exponential in this length of the game, which is about exponential in this H. So the first step will be looking at this hard instance and to see why those worst case instances are difficult and why we should not expect to find efficient solution for those kind of problems. So it turns out the hard instances are those POMDPs, although they call it partially observable things, but they're actually without any observations, or basically observations are dummy or trivial, which doesn't tell you anything about the underlying states. So we can think of this we can construct this hard instance as an underlying MDP with this dummy observation. Means no matter which states I'm in, I always give you the same observation. So in that sense, this observation doesn't tell you anything about the states. So in what follows, we will just specify what are those POMDPs. The POMDP is a standard POMDP called a combinatorial log, which is a two-state POMDP. We only have S0 and S1. And S0 is very special, so that I only take a very special action sequence. Here I should have a subscript, A1 star, A2 star, A3 star, till some AH star. I will stay in this S0. So no matter what other actions I'm going to take, I will always end up in S1 and leading to S1. Okay, so this is comparator log. So only special action sequence will stay in S0, and whatever other actions will lead to S1. And we're only gonna receive reward 1 in the very last step of S0. So in this case, I will receive reward 1. Otherwise, I will always receive S0. So in this case, we know the optimal policy is actually something state or observation independent. So we just input some fixed action sequence, A1 star, A2 star, till AH star, and we will end up getting reward 1. However, because we don't observe any observations, so we don't know whether we are in S0 or S1. So basically, we're completely in the dark. So this just become equivalent to something like we enter a password. Like we have no idea which underlying state is. We just need to enter the entire password of H length. And whether it's right, we receive the reward 1. When it's right, we receive reward 1. When it's incorrect, we receive reward 0. So clearly, there's no better way to learn this passcode other than trying all the possibilities. So this clearly will require some A to the H samples, which is basically the all possible, like possible number of a password. And in this case, clearly we should not expect we will able to learn it efficiently, like in polynomial samples. So we can conclude from this hard instance that POMDPs are hard if the emission structure do not distinguish two states or two mixture of states. In this case, like with two states, they have the same observation. So then it's just hard. Okay. So one way to address this problem is in order to develop efficient results for POMDP, we just rule out those hard instances. So the strategy is we just rule out this pathological instance that prevent efficient learning. So it turns out we know the pathological instance will relate it to this emission matrix, which is the probability of observation given the current states. We can view this emission matrix as a matrix which has a S by O, where each entry is this probability of O given S. Okay. So we know the hard instance says emission does not distinguish two mixture of states. Okay. That is, have two mixture of states, we have the same emission, we have the same observation distribution. So in mass, this will be equivalent to saying this rank of O is equal to S. If this rank is degenerate. If the rank is equal to S, then we will guarantee for any two mixture of states, we will able to distinguish by observation. So we will get rid of this like hard instance. So basically, we kind of see this is what we want to assume to get rid of this hard instance. So what we will assume in this talk is basically some robust version of this 4 rank assumption. Okay, so it says instead of just a 4 rank, we say the minimum singular value is slightly away from 0. It's lower bounded by alpha. So to avoid some like infinite closeness between this 4 rank matrix and like low rank matrix. Okay, so this is a single conditions we will assume throughout our talk, which will already guarantees we can efficiently learn POMDPs. Okay. And of course, there will also be a little bit more complicated setting, like over complicated setting, like when we assume this is sigma S, like single rank of this emission matrix is 4 rank S. This is already implicitly assumed the observation is greater than number of states. But there are also other scenarios, the observations might be less than states, which is now called overcomplicate. Basically, in that kind of a scenario, the high-level idea is we should not look at a single step observation. We should look at multiple step observation in the future. And we develop this emission matrix as this M matrix. And again, similarly, we can assume this singular value of this M matrix is greater than alpha. Okay. So basically, the takeaway is our assumption is basically just saying the emission matrix needs to be 4 rank. Just in the overcomplicate case, we need to look at a multiple step of observation instead of just a single step observation. That's all. Okay. So this actually is kind of quite standard that has been being frequently used in prior literature. But in the prior literature, it's unclear like whether this alone is sufficient to guarantee the efficient learning of POMDP. Our result will be the first to say this will be the case. Okay. So once we identify the problem structure, the second thing we will see is we need to develop efficient algorithms. So the high-level idea of why this algorithm need to be slightly different from what we have for the fully observed scenario is we can think the prior algorithm for the MDP is basically all of them are value-based algorithm, like value iteration, like Q-learning. However, in POMDP, those value-based algorithms may not be very good because, as we said, the value of policy will depend on the entire history, and the history is like all the possible combination of observation and action up to step H. So it will have exponential size. The value will depend on the entire history, so it also have exponentially size. So this in general is very bad because once the value has exponential size, then our samples will also have exponential size. So in POMDP, we'll use an alternative approach, which is a model-based approach. Well, in MDP, there are a lot of argument about like whether we should use model-free or model-based, but in POMDP, there are very good, solid reason of using model-based approach is because like regardless of the policy will require entire history, the model will always be specified by this transition and emission, where the transition and emission will always have polynomial size. So this is why model-based is kind of like preferred. So in our prior work with Akshay and Sham, we developed a spectral algorithm to estimate model, and so that we can learn some POMDP efficiently under this weakly revealing condition. So in our recent paper, we essentially say we can even do a more simple approach, which just combine this MLE, maximum likelihood estimation, which is very standard for like a model-based thing, and with optimism. We just combine those two, and which is sufficient to learn POMDP efficiently. Okay, so we will talk a little bit formally about the algorithm. So algorithm will maintain model parameters. In this case, for POMDP, model parameters is just transition and observation. So we just collectively denote them as a theta, and we will call the value function, which condition on this model parameter to be theta as v pi theta. Okay, so the algorithm is very simple. It just has 3 steps. We will always maintain a confidence set of the models of this T and O as B. So the first step is optimistic planning. That is, we will compute the optimistic model and the policy theta and pi, which maximize the value of policy pi condition on my model is actually theta. Okay, this is just like UCP, like up confidence bound. We do some optimistic planning first. And then second step, we'll just execute this optimistic policy to collect a trajectory, one trajectory, that is O1, O2, O1, A1, O2, A2 till OH, AH. And then the third step, we will put this trajectory into our confidence set. We update the confidence set. So the most important thing are in this step of how we update the confidence set. It turns out our confidence set construction is also very simple. We just compute the log likelihood of the data, and then we will maintain those models so that the log likelihood is just slightly worse than the maximum likelihood, MLE, and up to some tolerance beta. Okay, so this part, second part is the value of MLE, the value of maximum likelihood estimation, and we will say our likelihood can be just slightly worse than MLE up to some tolerance beta. Okay, this tolerance beta is basically some statistical tolerance because we only have finite samples. So we just quickly go over the guarantees. And the first guarantee is basically says in the under-complete scenario, the OMLE is guaranteed, our algorithm is guaranteed to find the epsilon suboptimal policies in the polynomial number of episodes. This polynomial is in number of horizon, number of states, number of action, number of observations, and also the accuracy epsilon, and also this alpha weakly revealing conditions. Okay. And in the over-complete case, we will also have similar guarantees, which we need to develop the M-step version of our algorithm, and which will also have this polynomial guarantees. So basically, we say our results provide the first line of sample efficient results that learn from interactions in rich class of POMDPs. This is weakly revealing POMDPs. Okay. And finally, I also want to mention a little bit of techniques. So the main bottlenecks of like our result, like our main challenge of our result or techniques is in this pigeonhole or elliptical potential lemma thing, which is basically optimism always require that kind of stuff. And while here in the POMDP, this basically condition is much weaker, so we will require a lot stronger that kind of lemma than the standard banded or MDP literature. So basically, in our paper, we developed some like new elliptical potential style of arguments, which use some L1 integral dimension and new techniques, so that which enable our results for this POMDP. And finally, I also want to mention a little bit of things beyond this POMDPs, beyond this weekly reading POMDPs. It turns out some similar ideas could also be extended to the multi-agent scenario where we have this partially observable Markov games, where each player has only local observations, and they may not even share observations, and those local observations only reveal some partial information about the states. So here we can basically prove similar results by saying if we have joint observation of all players, we could reveal the states. And we also have a similar algorithm, OMLE, but instead of doing optimistic planning, we will also do some optimistic calculation of the equilibrium, which is able to learn various equilibrium like Nash equilibrium or correlated equilibrium of this partially observable Markov game in polynomial samples. And our results are much more general than the classical results because it covers like a very special, very important class like imperfect information, extensive form games, which are standard models which people use to study poker games or some other like chess, some other games. And finally, we will be also able to extend this kind of results to a more intrinsic and general representation of partially observable model, which is called predictive states representation, and this result will be online soon in next few days. Okay, so this basically concludes my talk. I just want to summarize it. We provide the first line of sample efficient algorithms for learning large class of POMDPs. Okay, so different from prior results, this is like a sample efficient, so we only require polynomial samples, but it is a trade-off. We don't do a worst case of POMDP, but we identify a large class of POMDP, which makes sense in practice. Like we should expect only those class of POMDPs we can learn efficiently. Okay, so basically the condition is what we call weekly reading POMDPs, and the algorithm is just optimism plus MLE. And for future directions, we would like to identify some richer class of tractable partially observable problems. And also this entire talk is only about statistical efficiency. And we will also want to deal with computational efficiency. That is, we want to develop some polynomial time algorithms for this kind of problems. Okay, and I guess this concludes my talk. Thank you.
Thank you very much. Very interesting talk. So I would now ask if there are some questions from the audience. Please type them in chat or also from the other panelists and organizers. In the meantime, maybe I can ask one question. So let's say your talk was quite theoretical, right? And in the beginning, you had some applications mentioned. My question would be maybe about the pitfalls. What do you see typically done in research and modeled as MDP, but you think should be modeled as PMDP and partially observable MDP and solved like that? Like in the beginning, you have the hide and seek problem. I think that concrete paper actually used MDP, and both agents had the full state observation, and they came up with very interesting policies. But I think this is more appropriate to be modeled in real world scenarios as partially observable, right? So right. Where do you see usually pitfalls?
I think so this is regarding to the things we say that I think one of the important mechanism of solving POMDP is we need to reason about the belief over states. So instead of seeing the states, so I think then there's a difference between like how confident we are in the states. Maybe in this hide and seek problems, most times we're like when we combine all the agents' observation together, we're pretty certain about what is the underlying states of the system. And in that kind of a scenario, maybe the standard MDP stuff will be still work reasonable. But there are also some other scenario where basically by observation, we're highly uncertain about the states. Like we're already in the scenario where like one half probability here, one half probability there. For example, when we like need to study this poker game, if you don't treat it as an imperfect information, you will suffer extremely bad from like play. Like you just play some terrible strategy, which will never be win humans. So I think in those kind of scenario where like the underlying state is really uncertain from our observations, I think the dealing this kind of theory algorithm or like a theory developed for partially observable will have a significant edge over the standard thing. I think there are also some questions in the Q&A part.
Yes, so there are 2 questions in the Q&A so far. First one is the solvable class. You can read it.
Yeah.
Shall
Yeah, is this solvable class POMDPs defined by rank conditions? Is that possible to broaden the classes by using identifiability conditions
Of the dynamic system? I think that's a very good question, actually. So this is a rank condition on the emission matrix, but I would just want to mention this actually is weaker than even the identifiability condition. So usually, if you want to say the POMDP is identifiable, the identifiable people typically means I want to learn the emission and the transition, and then usually you need to assume in addition to this observability, like the 4 rank thing, you also need to assume something like I can visit all the states or something. But here we no longer need to assume that kind of visibility because we're in this exploration setting. So if some states are not visible, like no matter what kind of policy, I cannot visit those kind of states, it's okay for me to not learn the transition or emission there very accurately, because I'm anyway not going to visit them, and so that will not hurt our performance. So I would say our condition is weaker than identifiability.
Okay, there is another question. Thank you for your sharing the methods here are belief state-based techniques or not. Could we optimize those POMDP problems in belief state-based formulations, or avoid it because of the huge computation costs for
that's also
belief state?
Sorry for interrupting. Yeah, that's also a very good question. So yes, for POMDPs, you have 2 alternative ways for planning. One is like you can plan based on the entire history. The second one is, as he mentioned, you can plan on the belief states. But I think this is true for the planning setting where we know the model, like basically we know the transition and emission. But for this learning scenario, basically we just interact with unknown environment. We don't even know the transition and emission. So in that kind of scenario, estimating the belief states itself is a problem. Like if we don't have the transition and emission accurately, we cannot even estimate the belief states. Like our belief states will be far from the true belief states. And if we just do some inference based on this kind of inaccurate belief states, we'll incur like huge mistakes and huge errors, which is uncontrollable. This is why I think our framework is basically based on a history-based thing. I think belief states is potentially an interesting approach, but I think so far there's no good guarantees or whatever for like learning based on this belief states, just because of the problem I just mentioned. And also maybe there's a chicken and egg problem, like because estimating, as I said, estimating accurate belief states require accurate estimation of the transition, or like learning the transition and emission model, which in that kind of scenario we can already do very good with history-based policies. So this is my take about the difference between the 2 approaches.
Okay, maybe this is the last question. I think it's very interesting. Does then our work extend to complement information dynamic games where player reward parameters are private?
Yes, actually, so I haven't mentioned this, I only mentioned this in the very end. So in our paper, in this partially observable Markov games paper, I believe so basically we only have this local observations, and we said the setting, the reward is basically contained in observation. So yes, in that paper, we studied a scenario where each player has only local observation and local rewards, and we can still learn the equilibrium efficiently.
Okay, thanks for your great talk.
Thank you.